Okay, so today I want to talk to you about and
It's also in real analysis and also in complex analysis also. So the concept I want to talk today is a connected set and the connectedness. So I assume that before I start proving this theorem, I assume that you guys already know what connected set is and what is mean by this connected set. Okay, so let's get started. Okay, so I have the theorem, so let's put theorem. If we have XD is a metric space, this is the function. I assume you already know this also. And A sub I belong to Gi, capital I's, is a family of connected set. Okay, in other book, sometimes we use a collection of connected sets. So the family of connected sets is also has the same meaning as the collection of a connected set. It's the set that contain many other set in that set. Okay, so A sub I is a family of connected set in X. Okay, such that intersection of each member in this family connected set. So intersection of I sub I belong to capital I's, different from then union of A sub I belong to capital I's is connected. Okay, proof.
Okay, so how are we going to prove this? This is the information they given. So A sub I is a family, is a connected set. It means that each A sub I is connected set, and this one also given. So what we have to prove is we have to prove this. Okay, and how? All right, let's see. I think we can prove by contradiction, because we already know what the definition of disconnected. So we can prove by contradiction. So before we're doing that, let name it. Let A equal to a union of A sub I. By doing this, you make your life easier, because you have to deal with A only instead of union of A sub I. Okay, and we assume that A is disconnected or non-connected or not connected. It has the same meaning. Okay, and because A is disconnected, so there exists two open set. Okay, let me change the camera a little bit here. All right, so there exists two open set. Let's name it G1 and G2, such that A contained in G1 union G2 and G1 intersect G2 is empty set. A intersect G1 is not empty set, and A intersect G2 is not empty set. Okay, so this is where this is like a definition of disconnected set. So I just basically rewrite it from last time. Okay, so all right, what next here? So let's consider, because A sub I is a family of connected sets, so let's consider only one member of this family. So let's consider A sub I for some I for some I belong to capitalize. Okay. So because the member of this family so must be contained in this family, right? So A sub I must be contained inside A. Okay. And A is contained inside G1 union G2. Okay. Let's see. A sub I is a family of connected sets, so each A sub I for some I belong to capital I is connected set, right? So let's put a sin A sub I is connected. Okay, sin A sub I is connected. So it means that if A sub I, just think about it, if A sub I intersection G1 is empty set, and A sub I intersection, if A sub I intersection G1 is not empty set and A sub I intersection G2 is not empty set, it means that A sub I is disconnected, right? But because we have A sub I is connected, so either A sub I intersection G1 equal empty set. Okay, because it's connected, it's not connected. Okay, it's not disconnected, I'm sorry. Or A sub I intersection G2 equal empty set. Okay, alright, let's see. Okay, alright, what next? So we have A sub I intersection G1 equal empty set. Okay, and A sub I contain inside G1 union G2, and A sub I intersection G1 is not an empty set, so it means that it means that A sub I must be contained inside G2, right? Or A sub I must be contained in G1. Alright, let's take a couple minutes to think logically about this. Okay, if A sub I intersection G1 is an empty set, okay, is an empty set, equal empty set, it means that A sub I must be contained in G2, right? Because A sub I contained in G1 union G2. Or you can think that A sub I intersection G1 is equal empty set. It means that A sub I intersection G2 is not empty set, right? Or A sub I is contained in G2 because A sub I contained in G1 union G2. Okay, so this one I think you can get it over here. So we have A sub I contained G2 or A sub I contained in G1. Okay, all right. But A sub I is just one of the member of this family of connected sets. So how about we think all of the member of this family? So what happened? Okay, so okay. There are three cases. So let's go through the first case. So case 1, if A sub I, okay, if some A sub I contain G1 and some A sub I contain in G2. So there's some A sub I contain G1 and some A sub I contain G2. It means that what? It means that then the intersection of A sub I belong to capital I must be an empty set, right? Must be an empty set. It doesn't make sense, because some of them containing G1 and some of them containing G2, so the intersection of all of them must be an empty set. Maybe some of them, maybe a few of them it's not empty, but the intersection of all of them must be empty, and this is contradict to what we have over here. Okay, so they give an intersection of A sub I different from empty set, but we have over here intersection of A sub I equal empty set, so this is a contradiction. Okay, let's consider case 2. Okay, if all A sub I, all of them, if all of them contain in G1, so what's happening? What's happening over here? If all A sub I, it means if all member of this family of connected set contain in G1, then A equal to union of A sub I, okay, must be contained in G1. Must be contained in G1, right? Okay, because the union with all of them contained in G1, so the union of all of them must be contained in G1. Okay, and so A contained in G1. Okay, it means that, so which imply A intersection G2 must be an empty set, right? Must be an empty set. Must be an empty set. I'm sorry. Yep, must be an empty set, because they all of them are in G1. So the intersection with G2 must be an empty set. That makes sense. Okay. So, and this one also contradicts to this, because over here they say A intersection G2 must be an empty set, but we have A intersection G2 is an empty set. Okay, so this is a contradiction. Okay, case 3. So what if all A sub I contain in G2? So we're gonna think logically the same way as what we do in case 2. So if all A sub I contain in G2, then union of that must be contained in G2. If it contained in G2, then the intersection with G1 must be an empty set. But if the intersection with G1 is an empty set, so it contradicts to this one, right?
Contradiction. Okay, so all three cases we have a contradiction with what we assume at the beginning here. Okay, so it means what? So conclude here. So union of A sub I must be connected. Must be connected. Okay, because contradiction to what we have over here. We assumed before that it's not connected, but it contradicts to that, so it must be union of A sub I must be connected. Okay, so this is GED. So let me put this. Okay, so I mean that we already proved it. Okay, so next time I'm gonna prove another theorem also related to matrix space connected set, and later on we're gonna prove something with compact set and perfect set. Okay, thank you so much. Okay, so let's move up a little bit.